Very warm welcome to everyone for this Visimix webinar. I hope my voice is audible. If someone can confirm, it would be nice that my voice is
Yes,
audible.
we can hear you well. Please progress.
Thank you, Dr. Moshe. Thank you. So, as I said, this is the first webinar that we are having in India, wherein we have one of our customers, esteemed customers, Dr. Reddy's. And Dr. Mr. Somdev Ghosh from Dr. Reddy's has come forward and today to volunteer to help us understand how Vismix has helped Dr. Reddy's in terms of technology transfer and optimization and scale up activities. So, a little bit about Mr. Somdev Ghosh. I'll introduce our today's speaker to everyone, to the audience, and then let Mr. Somdev Ghosh take over and explain how Vismix has helped them. So, Mr. Somdev Ghosh, his designation in Dr. Reddy's is modeling and simulation specialist. He is involved in the technology transfer, wherein he is actively takes care of the process optimization, scale up, and tech transfer of semi-solid products from lab to manufacturing plant. He is also involved in formulation optimization of complex generics products and process optimization of API, improving the yield and productivity by optimizing the manufacturing route of numerous APIs and formulated products. Technical report writing, writing internal and external reports is part of his job. Also, troubleshooting and resolving the challenges during development and scale up of API and formulation of various dosages like oral solids, semi solid, topical products, and complex injectable dosages. So today here, Somdev, he also in Dr. Reddy's he'll tell you how he helps them in resolving the challenge using QBT and statistical tools, simulation and modeling tools, and characterization techniques. Somdev has handled over 50 projects in troubleshooting and improving the overall process of formulation and development. He is also involved in smart R&D, that is digital twins and automation. In fact, he is responsible for bringing in state-of-art technologies and PAT tools in the lab. As I said, development of digital twins for various unit operations in labs and manufacturing units, and automation of various manufacturing steps and processes in lab across functions. So we are honored to have Mr. Somdev Ghosh amongst us today, telling us his sharing his experiences and sharing his insights about the simulation software, so it can help all of us achieve our goals and our targets when it comes to technology transfer. Over to you, Somdev. Thank you so much for being here today with us and sharing your inputs. Over to you, Somdev.
Good afternoon. Thank you, Avigya, for such a detailed introduction. So my screen is visible, right? So,
Yes, Somdev. Yes.
So I have been part of Dr. Reddy's in the modeling simulation team for close to 5 years now, and I have a background of chemical engineering. And previously, I was working in Ikato and Bloom Energy before joining Dr. Reddy's. So here we are helping our different formulation teams and API teams with different modeling and simulation softwares to optimize their processes and scale up and resolve market challenges as well. So are you able to see the next slide now? I think there is some lag. So I will be talking on a few case studies where we have used Visimix software to help the optimization team and scale up. This is the first case study where we are supporting the fermentation team. So they have developed a process in their lab in Cambridge, R&D lab, and they have to take it to scale up in the plant present in China. So the plant in China has a scale of 23,000 liters, and the pilot lab in Cambridge is of about 50 liters. And the titer quantity obtained in the lab is 5 grams per liter, whereas in plant it's like you can see the graph is slightly over 2 grams per liter. So with the view of this plant of 23,000 liters, if there is decrease in the quantity of the titer, this will be a considerable loss in the yield and accordingly to the economics. So our aim was to obtain the similar titer concentration as compared to what was obtained in the pilot. So these are the model we have prepared using Visimix. So on the left you see the lab scale reactor, which is of 50 liters, and on the right you see the plant scale, which is of 23,000 liters. And from the diagram itself, it's evident that the geometrically those two vessels are not similar. So just to observe it from a bird's eye view is that we see that the plant doesn't have baffles. So because of this, you will see a very high vortexing. Just let's wait a couple of seconds for the slide to load. Yeah. So here you can see in this column, when there are no baffles in the plant reactor, there is very high vortex. So let me explain you the table here. So here are on the left side the parameters like hydrodynamic parameters, turbulence, gas distribution, and heat transfer inside the vessel. And the parameters we are talking about like operating speed, tip speed, mixing speed. And we have the pilot scale parameters in the plant when we had that 40 batch at the less titer was obtained. And here we are optimizing the baffles. So when initially there are no baffles in the plant reactor and they were operating the process at 20 revolutions per minute, we have captured what are the other parameters. Tip speed is about 3.5 meters per second. Then the mixing power, you can see that the mixing power is very less as compared to the pilot scale. Just because there are no baffles, there is very high vortex and swirling of the feed inside. Then the shear near the impeller is also very less, and eventually the gas distribution and heat transfer are also very poor. So then the next step was we had to optimize the number of baffles and the sizing of baffles. So we did some simulations with 2 baffles, 4 baffles, 6 baffles, and even the sizes of the baffle. So we came to know that with 4 baffles, the system is most optimum, and we have given the dimensions of the baffle in this slide here. So the next thing is that a very typical and thumbs rule is that whenever you are doing the scale up for fermentation, you have to consider the power per unit volume. You have to maintain same power per unit volume. So you see here in the pilot scale, the power per unit volume is 0.13 watt per liter. So when we use the same power per unit volume for the plant using 4 baffles, our speed comes to be 42 revolutions per minute. But we also have to consider other important parameters, like for example, how good is the gas distribution and how good heat transfer. Because in fermentation process, if the gas distribution is not there, so the cells present at the locations where fresh gas or oxygen is not coming, they would starve. They would gas or oxygen not coming again, they would starve. So we have to heat transfer, because if there is in fermentation process with a period of time, there is a heat generation, and that heat generation has to be taken out. Excess heat generation has to be taken out. So we check that at the speed where we will have the same range of mixing power, what will be the gas distribution and what will be the heat transfer. We found that at operating speed of 42 revolutions per minute, the gas distribution is really poor, and even the temperature distribution is really non-uniform. So this means that we have to increase our speed so that the gas distribution is uniform and the heat transfer is also uniform. But at what level we can go? So when we may compare the shear rate, in the pilot scale, the maximum shear rate which is in the zone of the impeller is about 7,000. Whereas in our operation, when we have same range of power to volume, the shear rate is about half of uh, the shear rate in plant. So there is a scope we can increase the speed to such an extent that we have the shear rate here, for example, in the range of the pilot scale. And so it is at this high shear rate, the cells do not die out. They are not sheared away by the impellers. So we estimated the operating speed, which can be at maximum value of the shear rate, and we then checked what will be the gas distribution here at this increased speed, and what will be the heat transfer at this increased speed. So from the Visimix, we found that uh, the gas distribution across the reactor and the heat transfer also are quite optimum and uniform. So then we suggested our team, so we should go ahead with this kind of operating speed. So what we infer from here that many times the thumb rule applied for chemical engineering, like you have a certain parameter like power per unit volume, we can just go on doing the scale up. But we also have to simultaneously check about what other parameters are more important. For example, in this case, we saw that even though we increase our operating speed and keep it equivalent to the power per unit volume, but it is not sufficient for distribution of the gas or maintaining the uniform heat transfer. So in that case, we have to use a speed such that the the cells in the fermenter are able to sustain, so that the shear rate is not higher as compared to the lab scale, and maintaining the gas distribution and heat transfer same. And also we have, like for example, many times we have to uh, help in the optimization of the vessel. For example, here we did for the number of baffles and the sizing of the baffles. So eventually with this kind of activity, our Titre concentration have increased, and the batch is under production in the plant. So I would be happy to take any questions here for this case study, or if you have any questions, we can also attend them at the end of the session. Okay, so with this, I will like to go to the second case study. The second case study is for one of our API production. The challenge was that during scale up, when the process was transferred from lab or pilot to the plant, the smaller size of crystals were obtained and a lot of fines were seen. So we had to troubleshoot that why are the smallest crystals are available in the plant. So what might be the reasons? That our thought process was that probably the speed is very high, which is causing the shear rate is very, and eventually causing the breakage of the crystals. So we prepared the pilot scale and plant scale models here using Visimix. So on the left, you can see the pilot scale design with the reclined blade turbine, and on the right, you can see the plant scale reactor fitted with an anchor. So again, the impeller in pilot and impeller in plant are different, and the geometry is also different. And in the in the pilot, you will see the average particle size range is from 250 to 300 microns. So these are typically D50 to D80 sizes. Whereas in plant, the particle sizes are lesser, 150 to 200 microns, and eventually these batches are kind of failing in terms of the size of the crystals. So when we do when we put the operating parameters in Visumix, we see that. So on the left hand side, you see the parameters. On this scale, this column, you will see the parameters used in the pilot scale, and eventually what parameters we are using to do the final scale up. Excuse me. So in this column, you see that the operating speed used in the plant is 48 revolutions per minute, and accordingly, they are obtaining the particle size of distribution, and we have identified the shear rate, the Reynolds number, and maximum energy of collisions between the particles, and how good is the suspension is. So in pilot, when they are using, they are operating at 48 revolutions per minute. So we are obtaining the desired particle size, and these are the derived parameters like the maximum shear which is present at the impeller level, then the Reynolds number, the energy of collision between the crystals, and what type of suspension is it. So initially, uh, same RP parameter was used, revolutions per minute, to scale up the parameter. So it was seen that when the same 48 speed was used in the plant, smaller particle size was obtained, and we found out that the shear rate, the maximum shear rate is almost 3 times that of the pilot scale. So this is quite high. Probably this is the reason the particles are not able to sustain the shear caused by the impeller is so high that probably this is causing the breakage of the particles, and eventually we are getting a lot of fines. Similar thing is obtained when we see Reynolds number. So the Reynolds number is also almost 3 times as high as the pilot. And when we see the maximum energy of collision, so this is also quite high, almost 25% higher than at the pilot scale. So with this, the thought process comes to us that the shear rate is quite high. So we have to maintain. So let's see what happens when we are running the operation at a speed where we will get the shear rate something similar to that of the pilot. So from here onward, these all are simulations. When we use operate when a simulation at a speed of 20 revolutions per minute, we find that the output is like in the similar region of the pilot, and the shear rate is also similar range, and the Reynolds number is also like in the similar range. But the suspension is partial suspension. This means that there will be a considerable amount of crystals deposited at the bottom. This is definitely a not suitable scenario. So our next thought process is that we have to find what speed the suspension is just suspended, that none of the particles remain at the bottom of the vessel. So this just suspended comes about 32 revolutions per minute, and we find that the shear rate are a little bit high, Reynolds number a little bit high. So again, we see that the next thing is that we check the energy of collision. So when we keep the revolutions at 38, we find that the max energy of collision is something close to the max energy of collision which we had in the pilot scale. And coincidentally, at the speed of 38, the operating speed like power per unit volume is also uh, quite similar to that of the pilot. So then we suggested a plan that operating speed should be higher than that of 32 and lesser than of 38. So even though at this highest speed, the shear rate is high, the Reynolds number is high as compared to the shear rate in pilot and Reynolds number, and probably the effect of these is seen in the size of particle as well. But the particle size we obtain with the speed rate of about 32 to 38, that is quite acceptable by the quality standard for this product. To summarize, what was our activity in this case study was that first we check at what speed the field batches were running, and what other does it give us in any inferences what might be the shear rate and what might be causing the attrition between the crystals and breakage of size. We found that the max shear is quite high, and but on the maximum shear rate, the suspension is not uniform, and there is some suspension crystals would be accumulated at the bottom. So then we calculated the just suspended speed, and then we took a factor of constant maximum energy of collision. Based on similar kind of thought process, we suggested the plan that the operating speed should be between 32, so which is the just suspended speed, and 38, which is the power per same power per unit volume. And with this, even though the average particle size was slightly smaller than that of the pilot scale, but that within the acceptable limit. So the plan to perform the batches with suggested speed. So with this, I have presented you two case studies. And incidentally, I have another case study from formulation side, which might be interested to a lot of people from pharma background. So I will be happy to share this case study as well. This case study talks about formulation of a cream, which is a line extension product of an already existing plant. So line extension means Dr. Reddy's has one product in market. So they want to launch another product of uh, similar type with the slight changes. For example, in this case, they are adding another excipient. I will just name it P.HCl. The challenge is that we have to find homogenization parameter. So since this is a cream, biphasic cream, oil phase is the dispersed phase and water phase is the continuous phase. So we had to use reciprocator model to find the homogenization parameters so that the droplet size match with the original cream. Excuse me. So the challenge we're finding here that the new compound, new excipient which was to be added is available in the form of a salt with HCl. So whenever this salt is added into the one of the phases, aqueous phase or the oil phase, it decreases the pH. And incidentally, in this stream, the viscosity builder is also pH dependent. So it acts perfectly in a certain range of pH. As the pH changes, the effect of viscosity builder changes. And one of the key parameters for responsible for the size of the dispersed phase is the viscosity of the oil phase and viscosity of the cream phase, water phase. So if their viscosity is changing, the droplet size of the dispersed phase will change, and accordingly the properties of the cream will change. So in this activity, we suggested our so the formulation team with what so they came to us with different formulation strategy where the addition of the excipient was at different levels so that uh, the viscosity of the oil and the aqueous phase is in the similar range of what was during the original cream. So, and based on that, we suggested them the homogenization speed and the homogenization time, with which we can find that the droplet size of the new line extension cream will be the same as that of the old cream. So here you can see the microscopy image of the original cream and the line extension cream at 40x magnification. So with this activity, we have tried to keep the homogenization speed, the process parameters of the new line extension product same as that of the previous product by by helping the formulation team to alter the addition of the new excipient. So that's all from my side. If you have any questions, please feel free to ask.
So thank you very much to present your activities with this mix and to see that in a very wide range of work you are using the software in order to understand what is the environment you are providing to your process to generate the result that you are looking for and to navigate between extreme conditions that can be no good for the process in equipment that are in the company. My question is regarding to the use in all these activities that you are doing. Um, what is the way that you are using in order to start to evaluate? So you are coming directly to the calculations, or you have some studies, and from these studies you come to calculations to advise. What is normally the way that you are using in order to progress with these conclusions?
Uh, Dr. Moshe, could you please repeat the question? I beg your pardon.
Yes, I see that you're using the software for a weight of applications, not only for one kind of activities. You have here gas liquid, and you have crystallizations, and you have some kind of emulsification in different fields, in the pharmaceutical industry and in the IPI. And my question is, if you can have some kind of methodology that you think you use when you need to solve this kind of situation, when you need to advise to your to people in Dr. Reddy what to do, if you have some kind of steps. So do this experiment, after that calculate, or opposite, calculate before, after that do the experiment. What normally you are doing in the company?
So normally we are in Dr. Reddy's support as a modeling simulation team, and we support different formulations like injectables, creams, ointments, and the API side as well. So we are trying to develop a process where for every scale-up activity, after it's being developed in the lab, while transferring it from lab to pilot, and from pilot eventually planned, so we will be involved to do the calculations. So right
You,
now, in many processes we are supporting, but still it is not a kind of essential part. But with time, I think using the modeling tool like Vismix will be an essential part, integral part of the entire process development.
so it will be advisable maybe to use the software at every change step, yes, because we don't know what will happen in the next step with the next equipment, but we know what is the hydrodynamic that will be good for the process. So if we will be able to understand what will be the range of work in the next step, we will be able to advise or to raise a red flag about the next step and try to focus ourselves in the solution. Yes, this is very interesting to see, and it was very interesting to see that even you are using different kind of agitators, you will be able, you continue to will be able to advise, because once you translate the equipment in the real hydrodynamic you are generating, the equipment is only the tool, but the main thing that happen inside the process is the environment you are generating with the hydrodynamic that you calculate and characterize for every process. So it was very interesting. If people have some question here in the forum, if people that are attending the meeting want to have question, please write in the chat to let me know. You are writing, for instance, Mr. Sriram Yalaman Chili. Do you want to ask question? I open. Okay, if you want, please open your microphone and ask.
Hello.
Yes, please.
Am I audible? Yeah, actually, in case study 2, crystallization scale up, what is the scale up parameter to standardize that PhD? Whatever what we want, 250 to 300 PhD. Na? So, what was the scale up? What is the scale up parameter from pilot to plant?
Somdev,
Hi,
you
Dr.
want
Moshe.
to answer?
So
Thank
yeah,
you.
so Initially, our process team thought of using the uh, operating speed to use as a scale-up parameter, but it was not a really good decision. And finally, we used that using the same uniform power per unit volume was helpful in doing the scale-up, even though the sizes are slightly less. But nevertheless, we also had checked o- the effect of maximum shear rate and just suspended. So right now, for a same kind of parameter can't be used for every process. The crystal size might withstand certain high shear. So actually here, power per unit volume has worked, but nevertheless, we also should check for the different parameters like the maximum collision, the shear rate as well.
Let me only give another input is that all of this is really a function of the process. For instance, if you are feeding some material to control the pH and the kinetics of this absorption of the pH of reaction of this material that you are feeding is very, very fast, you will need to consider the micromixing time, the circulation flow rate, the comparison between the flow rate and the feeding time that you are feeding your material. So really it's depending on the process. It's very critical with all these activities, the first question to understand what is the goal of the simulation and what you are afraid. If you are afraid about the impurity, if you're afraid about the distribution, and according to this goal, we will looking for what will be the mixing parameters that can influence the mechanism you are explaining. So it is very important to start with some assumption about what is the mechanism of the process we are using, or we have in our process, reaction, crystallization, and more. And based on the mechanism and the previous knowledge, we will be able to focus ourselves in mixing parameters like maximum shear rate, you suspended, or the last one here is energy power per volume, in order to advise better, okay? Because if we don't know the process, it's like we're entering to a room that is with no lights, and we're changing with no see, okay? If we don't see what we're doing, normally we will turn on the light and we'll see a lot of problems, okay? So it is very important to have some starting point of knowledge or assume or agree about what is the mechanism of the process. We have another one here, rising. Okay. You want to have another question, please? You can open the microphone.
Hello, actually, for this, any micro mixing and all calculate simulation is there for this whatever case study, micro mixing data
Yes.
and all.
Yes. If it's possible to calculate
So
or
that if you compare micro mixing data, if you compare micro mixing data, that parameter is able to consider as a scale up constant parameter or any other parameter, as you said, p by v. Okay, I understood, but micro mixing considered in this whatever case study or not? That doubt I have. Whatever you are projecting now, all parameters from pilot to plant, it is not correlatable. But I don't know how we achieved this.
yeah, no. Once you know what is the mixing environment you are applying, it includes all the levels. It includes the fluid elements that you are generating with the micro mixing level to the different zones in the tank, and to take a complete integral description of the tank. All of this is required to
Okay.
starting to think. But once you know the process and once you have some response, you can understand that what is the main influence. The main influence will come from the parameter. When you change, you apply sensibility. And for this, the best way to do is to have the fast calculations of every parameter that will be based in an acceptable model, reproducible model, and more. Yes, you are right. Any other questions from the attendees people? Okay, so thank you very much for with Somdev and Avijna. If you want to have some summary here, thank you from my side. Thank you very much. It is always very interesting to see how companies are implementing and using mixing to understand processes. And once we start to work with mixing, we understand how it's critical at every step and how we can save and be more professional in our answers to the company. And in these three cases, we see immediately how, in a right way to think, how simple it is to get conclusions and navigate in the activities required to give a good answer to the company. Avishna, please, you want to conclude? And of course, thank you
Yes.
very much to Dev to do the job. Very good job.
Thank you so much, Somdev. It was very in detailed case studies that you presented today, and in fact, it was very relevant to the industry that we are catering to, and the industry that the people from the industry who are present today could definitely relate to these challenges that even they face day in and day out during their operation. So, thank you so much for providing these insights of how Visimix has helped you in Dr. Reddy's, and how Dr. Reddy's has been using Visimix since past so many years, and utilizing it to the fullest of its capabilities. So I would urge and request each and every one of you to please go back and send us queries related to these case studies or whatever challenges that you're facing, so we can arrange a proof of concept activity for you in your industry, specific industry, and help you show how Visimix can help you. Also, we will share the recording of this with all of you, as well as the people. More people have registered for this, and for some reason could not attend this event today. So we will be sharing the recording of today's webinar with everyone, and you can go through it again and let write to us with your questions. Thanks once again for your
Thank
patience
you.
and your inputs and questions. Thanks, Dr. Moje, for arranging and organizing this. Always, it's a pleasure interacting with you and getting more inputs about Visimix.
Thank you
Thank you,
very
everyone.
much. And thank you,
Thank you
Somdev,
very
for the
much
good job
for this
you did
opportunity.
and for the nice presentation. Have a good time. Bye bye.
Bye bye.
Thank you.
Bye, everyone.
Thank you.
Thanks, Sundeep.